So we know how to do a rate law, and it tells you how the rate changes with reaction, with concentrations of the reactants. But what's going to be much more useful is to find how concentrations change over time. So during the life of the reaction, how can you figure out what the concentration will be? So we're actually going to take our rate law and use a little calculus, but luckily we're just going to use the result of it. We're not going to worry about how we got there. And we're going to figure out what we call integrated rate laws. And so they have to do with concentration over time. And then we actually can use it as a graphical method for determining the rate laws. All right, so the first order integrated rate law. So if a reaction follows first order, a first order concentration relationship, then we can use the first order integrated rate law. All right, so rate is always, remember, delta A over delta T. So the concentration over time T. And if it happens to be a reactant, which is what we're talking about in this case, it's negative. So the rate is the disappearance of the change in concentration of A over the change in concentration or change in time. All right, and we know that a first order rate law is equal to K concentration A to the first power. So what we're going to do. All right, so once we use calculus, we get the equation on the left. So if you integrate the concentration over time, so it's the natural log of the ratio of A at time t over A at time 0 equals negative kt. Because of the rule of logs, you can write the equation as it is in the blue here, where you can separate the AT over A naught. So depending on what you're trying to find in the equation, different forms of this equation can be used. So natural log of AT minus the natural log of A naught equals minus KT. Or you can also use the equation on the right, which is the E function is the inverse of the natural log function. So if you take the inverse of the natural log on both sides, you get the equation on the right, which is in black. And just to reiterate, AT is the concentration at time t. A naught is the initial concentration. Of course, T is time t. K is a constant that will be given to you. And then if you want to think of it, you may not know the exact concentration at time t and the concentration at time A, but you can look at the ratio AT over A naught as the fraction of A remaining at time t. So different ways of looking at this equation. But this is the equation you would use if you're ever whenever you have a first order reaction. All right, so let's look at an example. The decomposition of N2O5 to NO2 and O2 is first order. So that's all we need to know. It's first order, and we know the rate constant is 4.8 times 10 to the minus 4 inverse seconds. If the initial concentration of N2O5 is 1.65 times 10 to the minus second moles per liter, molar, what will the concentration be after 825 seconds? All right, so we have our equation. We use the second equation here because we're trying to solve for that concentration at time t, so we're undoing the log. You can do it any which way you want to, but we're undoing the natural log. All right, what do we know? We know K is 4.8 times 10 to the minus 4th. We know T is 825 seconds. And note that the rate constant is in inverse seconds and the time is in seconds, so they cancel each other out. So you just want to always be careful that your time and your rate constant have the same units. Otherwise, you'll have to convert one or the other. We know the initial concentration, N2O5 naught at time 0 is 1.65 times 10 to the minus 2, and so we're going to solve for the concentration at time t. So if we rearrange it, we have this. the concentration N2O5 at time t equals the concentration at time 0 times e raised to the negative kt. And then if we just plug in, we get this equation. Plug those numbers in and do the math. So substituting the information, we get this 1.65 times 10 to the minus second moles per liter times e raised to the negative 0.396. E to the negative 0.396 is 0.673. Multiply that by by the initial concentration, and we get the answer 0.0111 molar, or in scientific notation, 1.11 times 10 to the minus second molar. So just note that since this is your reactant and it should be disappearing, that concentration makes sense because it is lower than the initial concentration. Okay, so second order integrated rate law will be a little bit different. So remember that for a second order, rate equals K times A squared. Second order. Again, the rate is just the change in concentration of A over time. And this time, so if you integrate both sides of this equation, because you've got A squared, end up with this equation. So this is the integrated rate law over time, integrated over time, and it is 1 over the concentration at time t equals positive kt plus 1 over the initial concentration. A little bit easier to deal with, but just be careful with the fractions. So again, AT is the concentration at time t, A naught is the initial concentration, T is the time, and K is the constant. So you'll always be given all but one of these, and you just need to solve for the one that you're looking for. All right, so let's look at a second order example. All right, the decomposition of HI is given by the following reaction. The rate constant is 30 inverse molar per minute. How much time does it take for the concentration of HI to drop from 0.01 molar to 0.005 molar? All right, so let's see what we know. We know that the initial concentration is A naught is 0.01 molar. The final concentration at the time that we don't know, that we're looking for, is 0.005 molar. We know the K, so we can plug in what we know. So here's the equation, 1 over AT. This time I just brought the 1 over A naught onto the same side of the equation to make it easier, equals KT. So plug in those numbers, 1 over 0.005 minus 1 over 0.01 equals 30T. So go ahead and do the math. 1 over 0.005 is 200. 1 over 0.01 is 100. So 200 minus 100 is 100 equals 30T. Divide by 30. And we get time is 3.33. The units are minutes because our K value is in inverse minutes. So everything, so the molarity will cancel and we have our time in minutes. There's where they cancel out. So we can also use a zero order integrated rate law, and this is the integrated rate law for zero order is just A at time t equals negative kt plus A naught. So just plug in the t value and the initial concentration. You can find the concentration at any time t. We'll be probably focusing mostly on first order, second order, but zero order may pop in from time to time. This is a straightforward equation. Okay, so let's define the half-life. The half-life of a reaction is the time required for the reaction concentration to decrease by 1/2 to 1/2 of its initial concentration. So it's kind of a nice measure. How long will it take for half of it to disappear? For a first-order reaction, half-life is independent of the initial concentration. So we can actually plug this in. So what is a half-life? A half-life means that the concentration at time t, AT, is equal to half of what the A naught is. Okay, so if we substitute that into our first order equation, you can see here that AT is 1/2 A naught. So the natural log, the A naughts cancel. So you've got the natural log of 1/2 equals negative KT, T 1/2 being the time at halfway through when half of the concentration is gone. So the natural log of 1/2 is equals negative kT, and the natural log of 1/2 0.693. So T1/2 is 0.693 over K. So in order to find the half-life, you only need to know the K value. And it's just 0.693 over K. We can see what happens to the half-life of a first-order reaction. You can see here if you start, let's say the initial concentration is 0.0165. Let's say the half-life in this case looks like it's about, not quite 50, about 1400 seconds. So after 1400 seconds, the concentration has become half, 0.0165 divided by 2. And then after another 1400 seconds, the concentration goes from 0.0083 down to 0.0042, approximately half. And then after another half-life, it goes down by another half. So it just, each certain amount of time, whatever the half-life is, every time you get that far along, the concentration will decrease by half, and you get this, we call it an extinction curve, or a curve that's kind of starting out steep, but it starts to level off. So now, technically speaking, you never get to the end after a half-life and a half-life and a half-life. You just keep getting closer and closer to zero. In reality, for a chemistry, something in the lab, eventually you get so low that it's undetectable. And so after so many half-lives, usually we consider it zero, but I guess technically it never gets to zero. All right, so let's look at an example. Sulfuryl chloride decomposes in a first-order reaction. The rate constant, 2.2 times 10 to the minus 5 inverse seconds. What is the half-life at this temperature? Okay, so we know that half-life is just 0.693 over K. So if we plug K in and we solve for, we get, there we go, we plugged K in for it, and we get T1/2 is 3.15 times 10 to the 4th seconds, or 31,500 seconds. Okay, what about a second order reaction? The second order reaction, the half-life depends on the initial concentration, and so the half-life becomes larger as time goes on because it depends on the initial concentration, and since the initial concentration is changing, the half-life will become longer. So again, if we assume that AT equals 1/2 A naught and we plug it into our second order rate law, we can rearrange it and get this equation. So T1/2 just equals 1 over K times the initial concentration. So what you'll see is that each succeeding half-life is twice the length of its predecessor. So because A naught will become half, you're dividing by a half, so the time will become twice as long. All right, and then for a zero-order reaction, the half-life is, according to this equation, A naught over 2K. So actually, the half-life becomes shorter as the reaction proceeds, because now the A naught is in the numerator, and since that's getting smaller and smaller, the T1/2 will get smaller and smaller. All right, so we can actually use this data to graph and see. We can actually determine by looking at data if our equation is first order or second order by graphing. So I'll show you what I mean. All right, so let's take the first order equation and write it. Actually, I've write it like we did earlier on an earlier slide. And here we have natural log of AT. I think I wrote it on that slide, natural log of AT minus the natural log of A naught equals negative KT. And so this time we've brought the natural log of A naught on the right-hand side of the equation. Okay, so if you look at that, and you can see it's in the equation of a line, the y equals mx plus b is below it. So if you take x on the x-axis and plot time, and if you take the natural log of whatever the concentration is, so that would be natural log of AT as your y-axis, and you plot time versus natural log of A at whatever time you're talking about, you'll get this line. You'll get a line, a straight line if it's first order, and the slope of that line will be the negative k. So you'll be able to find what k is because the slope is negative k, and then the y-intercept is the natural log of A naught. So I think I have an example on the next slide. Okay, so again, like I just said, if you plot natural log of A versus time, you'll get a straight line for a first order reaction. All right, so here it is. So you can see here that on the first two lines, we've got time, and then we've got concentration of N2O5. Well, if we plotted that, we probably wouldn't get any kind of relationship. But if we take the natural log of the concentration, so take the natural log of 0.0165, and we get negative 4.104. Take the natural log of 0.0124, we get negative 4.39. So if we plot time on the x-axis versus natural log on the y-axis, and if it's a first order reaction, then we get a straight line as you see here. If we don't get a straight line, then you can be pretty sure that this reaction is not a first order reaction. All right, so we can also do the same thing for a second order. If we rewrite the second order equation as we see it here, it also has a y equals mx plus b formula. So again, if we take time on the x-axis, and this time if we plot 1 over the concentration at time t on the y-axis, we should get a straight line if it's second order, and this time the slope is just k, and the intercept is 1 over the initial concentration. So again, yeah, plot 1 over A versus time on the x-axis, 1 over A on the y-axis, and we get a straight line if it's a second order reaction. So this graph is showing us, this is showing sort of the difference. So they're giving you a bunch of information. There's the time versus the concentration of N2 over time, right? So at 0 time, the initial concentration is 0.01 molar. After 60 seconds, it's 0.00683 molar, etc. So then what they've done here is they wanted to see, is this data first order or second order? Does this reaction go by first order or second order? So in the first graph on the left, they've taken the natural log of concentration. So natural log of 0.01 is negative 4.605, and they've plotted it. And what you can see, that's the blue line on the left. The blue line on the left is not straight. So this tells us that this is not a first order equation. Does not fit the points well, and so it's not a first order reaction. But then if you take 1 over the concentration, so 1 over 0.01 is 100, 1 over 0.00683 is 146, and you plot those points, the plot of time versus 1 over the concentration gives me a straight line, so this tells me that this is a second order equation, second order reaction. All right, so here's just another example. Determine it by plotting. So butadiene, this reaction, 2C4H6 becoming C8H12. The following data were collected. Is this reaction first order or second order? And if so, and once you find out what is the value of K and what is the half-life. So these are 3 things that we want to figure out using this data. So again, what we're going to do is first plot time versus natural log of concentration. And so here I've taken time and I've done in the very right hand side the natural log of the concentration from the previous graph, and I've also done 1 over the concentration from the previous chart. So then we do the 2 plots, plot time versus natural log, and do time versus 1 over. We get the following graph. So the following graphs. The one on the left is time versus natural log, and you can see it's the blue line. It is not a straight line, and so this reaction is not a first order reaction. The right-hand line is time versus 1 over concentration, and you can see that it is a straight line. It does have the equation y equals 0.0613x plus 100. And since m is 0.0613, the slope of the line, that's the same as k. So k is 0.0613 inverse molar inverse seconds, because it is second order, so k has those units. And then finally, if we want to find the half-life is 1 over k times a naught. And so for this particular reaction, so 1 over k, 0.0613 inverse molar inverse seconds, times the concentration initial, which is 0.01 molar. And the molars cancel, and we have 1 over seconds, which gives us seconds in the end. So the half-life for this reaction is 1,630 seconds, or 1.63 times 10 to the third seconds. This is just a nice little table that summarizes all of our reactions. So we have the rate law for zero order, first order, and second order. For first order, notice that there is no concentration because it is independent. First order is a to the first power, second order a to the second power. The integrated rate law for zero order, for first order, and for second order, and then the half-life for those three, and then what a straight line will tell you.